There is an object in the universe that can release more energy in a fraction of a second than our sun will produce in hundreds of thousands of years. It is not a black hole. It does not tear space-time apart, and it does not swallow everything around it. Yet, its magnetic field is so intense that from far beyond the distance of the moon, it could wipe data from electronic systems. These objects are called magnetars. Its gravity is so strong that matter behaves in ways we cannot recreate on Earth. And inside it, the very rules that govern atoms are stretched toward their limits. For a long time, objects like this were little more than theory, rare, extreme, and poorly understood. Then something changed. We began detecting sudden flashes of radiation from deep within our galaxy. Brief, violent, precise, and in one extraordinary moment, we realized these flashes were not distant abstractions. They were measurable, observable, real. What scientists uncovered was not a failure of physics, but something far more intriguing. A place where physics still works, but only at its absolute edge. Tonight, we're going to explore one of the most extreme objects ever discovered. How it forms, why it behaves the way it does, and what it's teaching us about the limits of matter, energy, and the universe itself. Fonmot. When astronomers call something extreme, they are not describing a feeling. They are describing measurements. Energy released in a moment. Magnetic fields far beyond anything we can generate. Matter compressed to states we cannot reproduce on Earth. Magnetars stand out by every one of those measures. Start with energy. A magnetar can remain quiet for years, sometimes decades. And then, without warning, it releases a burst of energy so intense that it briefly outshines entire regions of space. These events last only fractions of a second. There is no slow buildup, no steady glow, just a sudden release. And then silence again. That silence is important. It tells us magnetars are not constantly violent. They store energy, hold it under tension, and release it only when something deep inside the star finally gives way. Then there is magnetism. The magnetic field of a magnetar is the strongest ever observed in nature. Earth's magnetic field shapes compasses and shields our atmosphere. A magnetar's field is trillions of times stronger. In that environment, magnetism is no longer a background effect. It becomes the dominant force. Charged particles cannot move freely. They are forced to spiral tightly along magnetic field lines, packed into regions where enormous amounts of energy are trapped and twisted. This magnetic stress is not static. Over time, the field slowly distorts, storing more and more energy until it suddenly rearranges itself. When that happens, the energy has to go somewhere. This brings us to the space around the star. A magnetar is surrounded by an intensely energized magnetosphere, a region where particles, radiation, and magnetic fields interact constantly. Here, space is not empty. It is active. Particles are accelerated. Radiation is produced, and the bursts we detect across the galaxy are born. Not from explosions in the usual sense, but from rapid magnetic reconfigurations. Sometimes, these outbursts are powerful enough to be noticed far beyond their point of origin. If a magnetar were close enough, much closer than any known today, its activity could disturb satellites, disrupt radio signals, and slightly alter Earth's upper atmosphere. This is not a warning. It is not a prediction. It is simply a reminder that these objects obey the same physical laws that govern our technological world, just under far more extreme conditions. And despite all this, magnetars are not black holes. They do not pull everything inward without limit. They do not hide behind an event horizon. They do not tear space-time apart. Instead, they compress matter and energy into an extraordinarily small volume and hold it there, balanced between gravity and magnetic forces so intense they push familiar physics to its edge. This is the key distinction. Magnetars do not break the laws of physics. They reveal how far those laws can be stretched. At this point, the question is no longer whether magnetars are extreme. That much is clear. The real questions come next. How can an object so small generate magnetic fields so powerful? What kind of star could collapse into something like this? And why does a magnetar release its energy in sudden bursts, like cracks forming deep inside a solid surface? To answer those questions, we have to go back to the moment when a massive star reaches the end of its life. Because the story of magnetars does not begin with magnetism. It begins when nuclear fuel runs out and gravity finally takes over. A massive star survives by balance. Gravity is always pulling inward, trying to crush the star into something smaller and denser. What keeps that from happening is energy, produced deep in the core through nuclear fusion. As long as fusion continues, the star can push back. For most of its life, that process is stable. Hydrogen atoms fuse into helium, releasing energy. The star shines, expands slightly, and holds its shape. But massive stars burn fuel quickly. They are hotter and brighter and far less patient than smaller stars like the Sun. Their cores exhaust hydrogen early, and when that happens, the balance begins to shift. The star responds by tightening its core. As pressure and temperature rise, new fusion reactions begin. Helium fuses into heavier elements: carbon, oxygen, silicon, each step requiring more extreme conditions than the last. For a time, the star adapts. It builds heavier material in its center while fusion continues in surrounding layers. Gravity pulls inward. Energy pushes outward. But this process has a hard limit. Eventually, the core becomes dominated by iron. Iron marks the end of the road for stellar fusion. Unlike earlier elements, fusing iron does not release usable energy. It drains it. At that moment, the star's engine stops paying for its own support. The core can no longer generate the pressure needed to resist gravity. And once that happens, there is no new reaction waiting to take its place. This is the point of no return. The collapse does not begin slowly. There is no gradual adjustment. Gravity takes over, and the core begins to fall inward faster than the star can respond. In a fraction of a second, matter is compressed to densities that defy everyday intuition. Atoms are forced together. Electrons are squeezed out of existence as distinct particles. The star does not choose what happens next. Physics does. What follows is not simply destruction, but transformation. The death of a massive star creates the conditions needed for one of the most compact objects in the universe, a neutron star. And under the right circumstances, that newborn neutron star can become something even more extreme. When the iron core collapses, it happens with astonishing speed. In just a few seconds, gravity pulls the core inward at a significant fraction of the speed of light. Matter is compressed so violently that familiar structures cannot survive. Electrons are forced into protons. Together, they form neutrons, releasing a flood of neutrinos as the collapse continues. What forms at the center is matter packed to nuclear density. At that point, the collapse finally meets resistance, not from heat or fusion, but from the nature of matter itself. Neutrons cannot be compressed without limit. Their quantum properties create a sudden stiffness at the core of the star. The inward collapse slams into this resistance and rebounds. That rebound sends a shock wave outward through the in-falling layers of the star. At the same time, escaping neutrinos deposit energy into the surrounding material. Together, these effects drive a supernova explosion. The outer layers of the star are blown into space, scattering heavy elements across the galaxy. For a brief moment, the explosion can shine brighter than an entire galaxy. But the most important outcome is what remains behind. At this point, everything depends on whether the newly formed core can support itself. If neutron pressure is strong enough to halt the collapse, a neutron star remains. An object with more mass than the Sun, compressed into a sphere only about 20 kilometers wide. If it is not strong enough, gravity continues its work. The collapse does not stop, and the result is a black hole. This difference is subtle, but decisive. A neutron star exists in a narrow window where matter can still resist gravity. Beyond that window, no known force can stop the collapse. A supernova does not guarantee a black hole, nor does it promise survival. It simply reveals which outcome the laws of physics allow. And when the balance holds, just barely, what remains is one of the densest objects nature can create. Imagine taking something with roughly the mass of our Sun and compressing it into a sphere the size of a city. That is a neutron star. From the outside, it does not look large or dramatic. Its diameter is only about 20 to 30 kilometers. You could drive across it in less than an hour if there were a road, and if gravity did not make that impossible. Yet inside that small volume is more mass than the entire Sun. This is where intuition begins to fail. Matter inside a neutron star is packed so tightly that ordinary comparisons stop working. A single teaspoon of neutron star material would weigh as much as a mountain on Earth. Not because it is made of exotic substances, but because gravity has crushed matter to a density we never encounter naturally. At this density, atoms no longer exist as atoms. There is no space for electron clouds, no familiar structure. What remains is a sea of neutrons pressed shoulder to shoulder, held together by gravity and the fundamental forces of matter. The effects of this compression extend far beyond density. Gravity at the surface of a neutron star is billions of times stronger than Earth's. If you could stand on its surface, your body would be flattened instantly. Not pulled inward, but compressed downward by sheer gravitational force. Light itself does not escape unchanged. Photons climbing away from the surface lose energy, stretched to longer wavelengths by gravity. Time passes more slowly there as well, compared to clocks far away. These are not theoretical ideas. They are predictions of general relativity, confirmed through observation. And yet, neutron stars do not collapse further, at least not always. They exist in a delicate balance. Gravity pulls inward relentlessly, but the quantum properties of neutrons push back, preventing the star from shrinking any further. This balance is not comfortable or stable in the way planets orbit stars. It is more like a system locked under enormous tension. Neutron stars spin rapidly, often dozens or hundreds of times per second. They cool slowly over time, radiating away the heat left behind by their violent birth. Some emit steady beams of radiation, sweeping space like cosmic lighthouses. Others remain quiet, barely detectable unless we know exactly where to look. What all neutron stars share is this: they represent matter pushed to the edge of what physics allows, without crossing the line into total collapse. And yet, even this is not the end of the story. because among neutron stars, there exists an even more extreme class. Objects where magnetism takes over, where energy is stored and released in ways that push physics closer to its absolute limits. A neutron star is what remains when a massive star collapses and survives. It is small, dense, and born in violence. But from that starting point, neutron stars do not all follow the same path. That is one of the most important ideas to keep clear. It is easy to imagine that after a supernova, every neutron star is essentially the same object, just a compact remnant cooling quietly in space. But in reality, neutron stars form a family. They share the same origin, yet behave in dramatically different ways depending on their spin, their environment, and, most importantly, the strength of their magnetic fields. The most familiar members of this family are pulsars. A pulsar is a neutron star that spins rapidly and emits beams of radiation from its magnetic poles. As the star rotates, those beams sweep across space like a lighthouse. When the beam crosses Earth, we detect it as a pulse, steady, clock-like, and repeatable. Some pulsars spin dozens of times per second. Others are slower, but their defining feature is consistency. They are powered primarily by rotation. As the pulsar spins, it gradually loses energy. Over time, it slows down, and the pulses weaken. Then there are neutron stars that do not live alone. Some are locked in binary systems, orbiting a companion star. In these systems, gravity can pull gas from the companion toward the neutron star. That gas forms a swirling accretion disk, heats up, and emits powerful X-rays. Here, the main energy source is not rotation. It is gravity, matter falling inward and releasing energy as it spirals down. These objects can be bright in X-rays, even when they are not particularly special in other ways. Their environment turns them into high-energy sources. And then there is a third category: rare, unstable, and far more extreme. Magnetars. Magnetars are neutron stars, but they are not simply pulsars with a stronger field, and they are not the inevitable next stage in the life of every neutron star. They are the exception. In a pulsar, rotation is the engine. The star is like a machine running on spin, clean, steady, gradually winding down. In a magnetar, the engine is magnetic energy. The star's magnetic field is so strong that it becomes the dominant force shaping what happens around it, and even what happens inside it. This is why magnetars can produce sudden, violent outbursts that pulsars do not. A pulsar may be astonishingly precise. A magnetar is astonishingly intense. That difference matters because it prevents a common misunderstanding. When people hear neutron star, they sometimes picture a single kind of object with one standard behavior. They assume magnetars are simply what all neutron stars become if given enough time. But that is not how nature works. Magnetars are not a stage. They are a branch. They form only under specific demanding conditions. Conditions that do not occur in every supernova. That is why they are relatively rare compared to pulsars. In other words, you do not get a magnetar just because you got a neutron star. Something extra has to happen. Something must set the magnetic field from strong to almost unimaginable. Something must push the star into a regime where magnetic stresses can fracture its crust, rearrange its magnetosphere, and release energy in bursts that can be detected across the galaxy. So when we talk about magnetars, we are not just talking about an extreme object. We are talking about a special outcome. one that tells us a great deal about how narrow the universe's pathways can be. Two neutron stars can be born in explosions that look similar from far away. Yet one becomes a steady pulsar, ticking for millions of years, and the other becomes a magnetar, quiet for long stretches, then suddenly erupting with extraordinary power. That raises the question that will guide us forward. If magnetars are not inevitable, if they are not simply the next step, then what creates them? What truly sets magnetars apart is not their mass, but their magnetic field. Magnetars feel alien, but their magnetism does not come from magic. It begins with a simple fact. Almost every star has a magnetic field. The sun does. Earth does. Even a quiet star, shining steadily for billions of years, carries magnetism within it, because hot, moving, electrically charged matter tends to generate magnetic fields. So the question is not whether magnetism exists. The question is how magnetism becomes extreme. Part of the answer is inherited. A massive star, the kind that will eventually collapse, already has a magnetic field of its own. It may not seem dramatic from far away, but the field is threaded through the star's interior like invisible lines under tension. Then the core collapses, and in that collapse, something important happens. The same amount of magnetic thread is suddenly forced into a much smaller space. This is the idea behind magnetic flux conservation. If magnetic field lines pass through a surface, and that surface shrinks dramatically, the field strength rises because the lines are concentrated into a smaller area. It is not a new field appearing out of nowhere. It is the same field, compressed. Imagine stretching a net across a wide frame. Then imagine squeezing that frame down to a tiny ring. The net did not change in material, but it became tighter, denser, and far more intense. A newborn neutron star is small on a cosmic scale, only tens of kilometers across. Compared to the enormous core of the original star, that is an almost unimaginable contraction. So even the ordinary magnetic field of the parent star can be amplified simply by being crushed inward. But compression alone is not enough to explain the strongest magnetars. For that, we need the second part of the story: rotation. A collapsing core does not just shrink, it spins up. As the core contracts, it can rotate faster and faster, the way an ice skater spins more rapidly when they pull their arms inward. In the first moments after birth, some neutron stars may rotate in milliseconds, hundreds of turns per second. That is not just fast. It is a violent kind of motion. And when you combine extremely rapid rotation with electrically conducting matter, you create the conditions for a dynamo. A dynamo is a process that converts motion into magnetism. We see weaker versions of it on Earth, where moving liquid iron in the outer core generates our planet's magnetic field. We see a more complex version on the Sun, where churning plasma drives magnetic cycles, sunspots, and solar flares. A newborn neutron star can take this idea to an extreme. Inside it, you may have hot, conductive material in motion, stirred by convection, spun by rapid rotation, and distorted by the chaos of collapse. In those first seconds, a dynamo can amplify the magnetic field far beyond what compression alone would produce. This is the heart of magnetar formation. Not every neutron star is born spinning that fast. Not every collapse produces the same internal turbulence. Not every star begins with the right magnetic seed. The conditions have to align. That is why magnetars are rare. A pulsar can be born with a strong field and a fast spin and still remain, at its core, a rotation-powered lighthouse. A magnetar requires something more demanding, a magnetic field that becomes the dominant energy reservoir of the star itself. That is why magnetars are not the next step for neutron stars. They are not what happens automatically with age. They are what happens when birth is unusually extreme. By the time the supernova debris expands into space, the magnetar's fate may already be set. Its magnetic field was created and amplified in the earliest moments, before the remnant cooled, before the star settled, before anything could become stable. And once such a magnetic field exists, it does not simply sit there quietly. It evolves, it twists, it stresses the crust and loads the magnetosphere with energy. And sooner or later, that energy has to be released. If you're still here with us, thank you. We truly appreciate you taking this time to explore the universe together. We hope this video has given you something valuable, not just information, but a clearer way of seeing how vast and fascinating the cosmos really is. We're always listening, always learning, and always trying to make these journeys deeper and more meaningful for you. If you'd like to support what we do, a simple like, a subscription, or sharing this video helps more than you might think. And without keeping you waiting any longer, let's continue our journey into what comes next. Magnetars feel like they should be everywhere. They are dramatic. They release bursts that can be detected across the galaxy. They push physics toward its limits. And yet, in a galaxy as vast as the Milky Way, magnetars appear to be uncommon. Astronomers have identified only a few dozen confirmed magnetars and strong candidates. That is a tiny number compared to the broader population of neutron stars, because neutron stars themselves are not rare. Over the Milky Way's history, supernovae have likely created vast numbers of them, possibly millions. So why do magnetars stand out as exceptions? Part of the answer is birth conditions. A magnetar is not simply a neutron star that gets stronger over time. It seems to require an unusually extreme beginning. The parent star must be massive enough to collapse into a neutron star, but not so massive that it collapses straight into a black hole. The newborn core must spin rapidly enough to support a powerful dynamo in those first seconds. And the magnetic seed, inherited from the parent star, must be strong enough to be amplified into something extraordinary. That is a narrow doorway. Most neutron stars do not pass through it. But rarity is not only about formation, it is also about visibility. Magnetars are most noticeable when they are young, when their magnetic fields are strongest and most unstable. That is when the crust is under stress, the magnetosphere is loaded with energy, and the star is most likely to erupt. Over time, that activity fades. The magnetic field slowly decays. The outbursts become less frequent. The star can settle into a quieter state, still extreme in density, still compact, still real, but no longer announcing itself with bright flashes. Which means many magnetars may exist in the Milky Way without calling attention to themselves. They could be out there, silent and aging, detectable only if we know exactly what signature to look for. Some may be hidden by distance, others may be hidden by dust, and many may simply be hidden by their own quietness. So the magnetars we know are not necessarily the full population. They may be the visible tip of a much larger, mostly unseen group. That thought changes the way we interpret what we observe. Rarity does not mean insignificance. In fact, the reason magnetars matter is precisely because they are so extreme that nature produces them only under special circumstances. They are not common machinery of the galaxy. They are fireworks. Brilliant, intense, and short-lived. And when magnetars are young, their magnetic fields are anything but stable. From the outside, a magnetar appears calm. It is small, compact, quiet for long stretches of time. But beneath that still surface, something very different is happening. A neutron star has a solid crust, a thin outer shell only a few kilometers thick. Compared to the size of the star, it is almost negligible. Compared to anything on Earth, it is unimaginably strong. This crust is made of matter packed so tightly that atomic nuclei are pressed into rigid, ordered structures. It is not rock in any ordinary sense. It is neutron-rich material arranged under pressures far beyond anything we can test in laboratories. And through this crust, magnetic fields pass freely. In an ordinary neutron star, those fields are strong but manageable. In a magnetar, they dominate everything. The magnetic field does not simply sit in place. It twists, it evolves, it slowly rearranges itself over time. Those magnetic field lines are anchored deep inside the star and thread outward through the crust and into space. As they shift, they pull on the crust from below, not all at once, but steadily, relentlessly. The crust tries to respond. It can flex slightly. It can adjust to small changes. But it cannot flow like a liquid. It cannot stretch indefinitely. So stress begins to build. This process is slow and silent. There is no warning light, no steady increase in brightness. From far away, the magnetar may appear completely inactive. But internally, the magnetic field continues to twist and tighten, loading the crust with tension the way a spring is wound tighter and tighter. The important point is this: the stress does not come from gravity. Gravity already did its work long ago when the star collapsed. What is happening now is driven almost entirely by magnetism. The crust is being pulled sideways, distorted by forces far stronger than those that shape planets or even ordinary stars. And while the crust of a neutron star is incredibly rigid, it is not unbreakable. There is a limit. Eventually, the crust reaches a point where it can no longer respond smoothly to the changing magnetic field beneath it. It cannot bend any further without failing. And when that limit is reached, the release is not gradual. All the energy that has been stored silently, sometimes for years, is released in an instant. This is the moment everything has been building toward. The magnetar does not explode because it is unstable by nature. It erupts because stress has been accumulating patiently and invisibly until the structure holding it can no longer cope. What follows is sudden, violent, and powerful enough to be detected across the galaxy. The magnetar's outbursts do not come from nowhere. They begin the way we described it, quietly, a magnetic field twisting over time. Stress building inside the crust, tension accumulating in a structure that cannot bend forever. For long periods, nothing happens. And then the crust finally gives. This is what astronomers call a starquake. It is not an earthquake in the usual sense. There are no tectonic plates, no oceans, no shifting continents. But the idea is similar. A rigid surface under stress reaches its limit, and it breaks. When it does, the change is sudden. The crust cracks or slips, releasing tension that may have been stored for months or years. And because the magnetar's magnetic field is anchored through the crust, that sudden shift does not stay confined to the surface. It jerks the magnetic field lines. Field lines that were slowly being twisted are suddenly forced into a new geometry. The magnetic structure above the star is disturbed, stretched, and distorted in an instant. And then something happens that can release enormous energy almost immediately. magnetic reconnection. In ordinary language, reconnection is what happens when magnetic field lines snap and reattach into a simpler configuration. They break, they reconnect, and in doing so, they convert stored magnetic energy into motion, heat, and radiation. You can think of it like a tangled rubber band being released. When the band is twisted, it stores energy. When it snaps into a less tangled shape, that stored energy is released quickly. The difference is scale. In a magnetar, the rubber band is a magnetic field so strong it can dominate the motion of matter, and the energy released can be extraordinary. This is why magnetar bursts are brief but intense. The energy is stored slowly but released fast. Once reconnection begins, it can cascade. A small region rearranges, which forces neighboring regions to rearrange. In seconds or less, an entire section of the magnetosphere can unload energy that took a long time to accumulate. What we observe from far away is a flash. Often, these are short bursts, brief, sharp spikes of X-rays or gamma rays, lasting fractions of a second. They may occur in clusters, then stop. They are violent in their intensity, but they are not constant. And then, rarely, there is something else. A giant flare. These events are far less common, but they reveal what magnetars are truly capable of. A giant flare can begin with an initial, extremely bright spike, followed by a longer, fading tail that can last minutes, often modulated by the star's rotation. What matters here is not the exact shape of the light curve. It is the underlying cause. This is not a nuclear explosion. The magnetar is not burning fuel the way a star does. It is not running on fusion. Its outbursts come from magnetic energy alone. Stored, stressed, and then suddenly released when the crust shifts and the magnetosphere rearranges. So the violence is real, but it is not chaotic. It follows a chain of cause and effect. Stress builds, the crust fails. Field lines snap and reconnect. Energy escapes as high-energy radiation. And then, for long periods, the magnetar becomes quiet again. That pattern, long silence, sudden release, is one of the signatures that tells astronomers they are not looking at an ordinary pulsar. They are watching a magnetic system operating at the edge of what nature allows. Which brings us to the next question. If these bursts can release so much energy so quickly, has anything like this ever been noticed close to home? Has a magnetar outburst ever left a measurable fingerprint on Earth? Because on rare occasions, this release is powerful enough to be noticed far beyond the star itself. A neutron star is not just heavy, it is dense in a way that changes what matter is. We already use the comparisons, the city-sized star, the teaspoon that weighs like a mountain. But the deeper point is this. Inside a neutron star, atoms cannot remain atoms. In normal matter, electrons occupy space around nuclei. That space is what gives ordinary objects their volume. But under the crushing gravity of a neutron star, that structure collapses. Electrons are forced into tighter and tighter states until they can no longer be packed further without changing the rules. This is where quantum pressure begins to matter. In a white dwarf, electron degeneracy pressure can resist gravity. It is a quantum effect. Electrons cannot all occupy the same state, so they push back when squeezed. But in a neutron star, the pressure goes deeper than electrons. Electrons are driven into protons, forming neutrons, and now it is neutron degeneracy pressure that resists the collapse, along with a strong nuclear force acting between particles at extremely short distances. This is not chemistry. This is matter at nearly nuclear density. And at those densities, one question becomes unavoidable. What is the recipe of matter when it is packed this tightly? Physicists describe that recipe with something called an equation of state, the relationship between pressure, density, and temperature inside the star. In simple terms, it tells us how matter responds when you squeeze it past every familiar threshold. The problem is, we do not know the exact equation of state for neutron star matter. Not because the math is too lazy, because the conditions are too extreme. We cannot recreate nuclear density matter in a lab and hold it steady long enough to measure it the way we can measure ordinary materials. We can collide particles at high energies, but that is not the same as building a stable object made of that matter and watching how it behaves under gravity. So we are left with models. Some predict stiffer matter that resists compression. Others allow softer matter that compresses more easily. And deep inside, there may be even stranger possibilities. Exotic particles, new phases, arrangements we have never seen. This is where magnetars become more than a curiosity. They are natural laboratories. They push matter and fields into regimes that sit beyond our technology. They give us signals, spin rates, cooling behavior, bursts, vibrations that help constrain what the interior can be. So when we study magnetars, we are not only chasing dramatic outbursts, we are testing the behavior of matter itself at the edge of what physics allows. And at these densities, matter begins to arrange itself in unexpected ways. When you push matter to nuclear density, it doesn't simply become solid in the way we imagine. It begins to organize itself. And one of the strangest, most memorable ideas in neutron star physics has an almost playful name: nuclear pasta. Not because it is soft, not because it is food, but because, under extreme pressure, nuclear matter may arrange itself into shapes that resemble pasta: thin strands, flat sheets, and clumped knots. Physicists talk about phases with names like spaghetti, lasagna, and gnocchi. The names sound light, almost humorous, but the reason these shapes form is serious physics. Inside the crust of a neutron star, two forces compete. The strong nuclear force wants protons and neutrons to stick together at very short distances. Meanwhile, the electric force, the Coulomb repulsion between protons, pushes charged matter apart. Under ordinary conditions, atoms and nuclei settle into familiar structures. But under the crushing density of a neutron star, there is no ordinary. The system is forced into a compromise. Instead of neat, spherical nuclei, matter may stretch into long nuclear strands, or flatten into layered sheets, or break into clumps arranged in repeating patterns. It's not random chaos. It is matter finding the lowest energy arrangement available under extreme constraints. And if nuclear pasta exists the way models predict, it is not just a curiosity. It could affect how a neutron star behaves as a physical object. For example, the structure and stiffness of the crust influence how the star vibrates. They influence how stress is stored and released. They may even shape the way starquakes propagate through the crust, how cracks form, how energy travels, how the surface responds when the interior shifts. In other words, the strange architecture of matter may be part of what makes magnetars behave the way they do. This is not science fiction. It is an attempt to describe real matter under real conditions. Conditions we cannot build in a lab, but that exist naturally in the universe. And the twist is that the funniest name points to something profound. At the edge of physics, matter stops behaving like matter. It becomes structure guided by nuclear forces. And in magnetars, the strangeness doesn't stop at matter. because once the magnetic field reaches magnetar's strength, even empty space does not behave the way we expect. A magnetar does not just push matter to extremes, it pushes space itself. Near a magnetar, the magnetic field becomes so intense that it exceeds anything humans can generate on Earth by many orders of magnitude. These fields are not just strong. They are strong enough to reach a regime where the familiar idea of empty space begins to fail. In everyday life, we treat space as a backdrop, a quiet stage where matter and energy move around. But in quantum physics, space is never truly empty. Even in a perfect vacuum, particles flicker in and out of existence. These are not particles you can capture or isolate. They are virtual particles, temporary fluctuations allowed by quantum mechanics. Normally, these effects are subtle. They average out. Space appears calm and transparent. A magnetar changes that balance. In an ultra-strong magnetic field, those fleeting quantum fluctuations begin to behave differently. The field interacts with the vacuum itself, subtly rearranging how virtual particles appear and disappear. This phenomenon is known as vacuum polarization. In simple terms, the magnetic field makes empty space behave more like a medium than a void. Light traveling through this region no longer behaves as it would in ordinary space. Its polarization can change. Its path can be altered ever so slightly. Different orientations of light propagate differently, as if space itself has acquired structure. The effect is small, but measurable. This is not science fiction. These behaviors are predicted by quantum electrodynamics, one of the most precisely tested theories in physics. For decades, vacuum polarization existed mainly in equations and thought experiments, because the required field strengths were far beyond laboratory reach. Magnetars provide those conditions naturally. Around them, space becomes an active participant in the physics. Not because new laws appear, but because known laws are pushed into regimes where their consequences are no longer subtle. What matters here is perspective. We often imagine that the strangest physics must happen deep inside exotic matter, inside black holes, or within unfamiliar particles. But magnetars show us something unexpected. Sometimes, the most unfamiliar behavior comes not from matter, but from the space between things. By observing how light behaves near magnetars, astronomers can test quantum theories under conditions no experiment on Earth can replicate. They can look for signatures that confirm, refine, or challenge our understanding of how fields and particles interact. In that sense, magnetars are not just astrophysical curiosities. They are laboratories. They allow the universe itself to run experiments for us. Experiments that take place at energy scales and field strengths far beyond human engineering. And the result is quietly humbling. Even when nothing is there, even when we think we are looking at empty space, physics is still at work. Nothingness is no longer nothing. And magnetars remind us that the universe still has ways to surprise us, not by breaking the rules, but by revealing just how far those rules can stretch. Not every discovery begins with certainty. Sometimes it begins with a signal, brief, bright, and out of place. A flash appears in the data. It lasts only a moment. It comes from far beyond our galaxy. And at first, no one is sure what to call it. It doesn't behave like a supernova. A supernova builds, brightens, and then fades over days or weeks. This signal is too fast for that. Too sharp, too clean. It doesn't behave like a pulsar. Pulsars repeat. They pulse with rhythm like a rotating lighthouse. This was not rhythm. It was a single, isolated event. And it doesn't look like a simple instrumental glitch either, because it appears in a way that has structure, timing, and energy consistent with a real astrophysical source. So the first reaction in the scientific community is what you would expect: skepticism. People check the equipment. They check the pipeline. They check whether the same pattern appears in other instruments. They ask the most basic question first: is this real? Because the universe is noisy and our detectors are sensitive. A cosmic ray hitting a sensor can create a spike. A software artifact can look like a burst. A calibration error can mimic an explosion. But the more the data is examined, the harder it is to dismiss. The signal is short, but it is also bright. Bright enough to stand out even from an immense distance. That combination, brief and powerful, is what makes it so unsettling. Not because it feels like danger, but because it forces a new category. If it's real, something released an enormous amount of energy quickly, and did so far away in another galaxy. That immediately narrows the list of suspects. There are only a few known astrophysical processes that can produce extreme luminosity on short timescales. Some involve black holes, some involve neutron stars, some involve explosive events we still do not fully understand. But this signal doesn't fit neatly into the usual boxes. Its time profile is wrong for a supernova. Its lack of repetition is wrong for a typical pulsar. Its energy appears too concentrated for many standard models. So scientists do what they always do when the sky refuses to cooperate. They compare it to what they know. They try older explanations first. They test whether it could be a strange type of supernova. They ask whether it could be an accreting black hole flaring briefly. They explore whether it could be a highly unusual pulsar event. And still, something doesn't fit. The location adds another layer of attention, because the signal comes from a distant galaxy, meaning it has traveled across intergalactic space to reach us. It is not a local oddity. It is not something inside our own backyard. It is an event that took place in an environment we cannot visit and cannot influence, yet we can still measure it. Detected, but not understood. That is the moment when astronomy becomes investigation. The discovery stops being "we saw a thing" and becomes "we have a puzzle." And puzzles create momentum, because if this signal is real, and if it truly sits outside known categories, then it may be pointing to a process we have not fully recognized yet, or a rare event we have underestimated, or an extreme object behaving in a way we did not expect. So the response is not panic. It is focus. Astronomers begin to watch more carefully. They comb through archives for similar events. They tune their instruments and surveys to catch the next one. Because one signal might be an anomaly, but two signals become a pattern, and a pattern becomes a new piece of physics. This is how newborn categories are created in astronomy, not by a single headline, but by repeated evidence that refuses to fit the old explanations. And to understand this signal, astronomers had to look in a very specific direction, not toward ordinary stars, not toward steady pulsars, but toward the most extreme stars, and what they do in the chaotic moments after they are born. Once astronomers accepted the signal was real, the next step was careful comparison. Not guesswork, not a dramatic leap, a process of elimination. Because in high-energy astronomy, many objects can produce bright flashes. The question is not, what is powerful? The question is, what matches the timing, the shape, and the energy pattern? One possibility was a black hole. Black holes can flare when they feed, when gas falls in and heats up. but those events usually have signatures that linger. They often involve longer-lived accretion or repeated activity, or a spectrum shaped by matter spiraling into an event horizon. This signal didn't behave that way. It was too short, too clean, and its brightness didn't come with the usual feeding fingerprints. Another possibility was a pulsar. Pulsars are neutron stars, and they can be energetic. But pulsars tend to produce regular pulses powered by rotation. Their output is often stable, patterned, and persistent, more like a beacon than an explosion. This wasn't a beacon. It looked like something that switched on violently, then began to fade. That fading matters. Some signals don't just appear and vanish. They peak, then decline in a way that reflects an internal engine losing power or settling into a new state. And that is where the newborn magnetar model becomes compelling. A newborn magnetar would be extreme from the start. It would be born with rapid rotation and an enormous magnetic field. In its first moments, it would have a large reservoir of energy, stored in rotation and, more uniquely, in magnetism. But a magnetar cannot hold that energy quietly. A field that strong twists, evolves, and drains energy into its surroundings. A rapidly spinning newborn object can also lose rotational energy quickly, especially if its magnetic field couples strongly to the environment. So the expected behavior is not steady. It is intense at first, then decaying, in other words. A bright, short-lived signal that fades in a structured way is exactly what you might expect if you were watching an extreme neutron star in its earliest phase. Before it calms, before it becomes quiet, before it blends back into the background of the galaxy. And newborn is the key word here. A mature magnetar can produce bursts, even giant flares. But those are episodes in a long life. A newborn magnetar is different. It is an engine still settling into existence. The physics is happening at full volume. The field is at its strongest. The system is far from equilibrium. That makes it easier to detect and easier to connect to a physical model, because the signal carries the imprint of a star switching on. That is why this event drew attention. Not because magnetars are mysterious, but because the timing, the intensity, and the decline fit a picture that had long existed in theory. A magnetar in its first moments, burning through an extreme energy budget as it stabilizes. If that interpretation is correct, it means something rare. It means magnetars are not only inferred from their aftermath. We may have seen one ignite. For the first time, theory and observation appeared to meet. If this kind of signal truly marks a newborn magnetar, then the significance is larger than a single event. It changes how we think about magnetars in the first place. For a long time, magnetars were treated mostly as finished objects, compact remnants we discovered after the violence was over. We saw the bursts. We measured the fields indirectly. We studied their behavior and maturity. But birth is different. Birth is where the physics is loudest, fastest, and least forgiving. It's where the conditions that create magnetars are revealed most clearly, before time smooths everything out. A newborn magnetar model forces a new kind of question, not just what magnetars do, but how magnetars turn on. That matters because it reshapes formation models. If magnetars can be detected in their earliest moments, then we can begin connecting them directly to the environments that produce them. The mass of the parent star, the rotation of the collapsing core, the structure of the surrounding debris, and the strength of the magnetic seed field before collapse. Instead of guessing backward from the adult object, we can watch the beginning and compare it to theory. It also matters because magnetars sit at the crossroads of other mysteries. One example is fast radio bursts, FRBS. FRBS are brief, intense pulses of radio waves that appear from across the universe. For years, they were one of the cleanest detected but not understood signals in astrophysics. And while not every FRB is explained, magnetars have become one of the most serious candidates, especially after observations linked at least some bursts to magnetar-like activity. A newborn magnetar connection doesn't solve the entire FRB puzzle, but it strengthens something important: the idea that highly magnetized neutron stars can produce detectable, transient signals across vast distances, and that the most extreme behavior may happen early in their lives. The connection to supernovae is just as important. If a newborn magnetar forms inside expanding supernova debris, it could inject energy into that debris. It could alter the brightness and evolution of the explosion. It could help explain why some supernovae appear unusually luminous or behave in ways that standard models struggle to reproduce. In other words, magnetars may not be passive leftovers. In some cases, they may be active engines shaping the aftermath of stellar death, and that pushes the implication outward. Because when we understand how stars die and what they leave behind, we understand how galaxies evolve. We understand how heavy elements spread into space. We understand how the raw material for planets and life moves through cosmic time. So this is not just a new detail in a niche corner of astrophysics. It is a new window, a new way to connect high-energy signals to real physical events. Collapse, birth, and extreme field switching on. And perhaps the most exciting part is not what we already saw, but what it suggests we might see next. Because astronomy is entering an era where transient events, brief, rare, and powerful, are no longer lost in the noise. They can be caught, tracked, and compared in real time. But not all magnetars announce themselves so loudly. When we talk about magnetars, it's easy to picture the ones that announce themselves, the ones that burst, the ones that flare, the ones that leave bright spikes in X-ray and gamma-ray data. But that picture is biased, because astronomy is not a census. It is a searchlight. We only notice what produces a signal strong enough, clear enough, and timed well enough to cross our instruments. And magnetars do not always cooperate. We have identified only a small number of confirmed magnetars and strong candidates. Yet there are good reasons to suspect that this is not the full population. It may be only the loudest fraction. A magnetar is easiest to detect when it is active, when its magnetic field is twisting, stressing the crust, and releasing energy in bursts. Those events create unmistakable signatures. But magnetars are not continuously erupting. Much of the time, they are quiet. And when a magnetar is quiet, it can be surprisingly difficult to distinguish from other compact objects, or to detect at all. A pulsar, even a faint one, helps us by repeating. It flashes with regular timing, like a lighthouse. We can fold the data, stack it, and gradually pull the signal out of noise. A quiet magnetar doesn't offer that. It may not pulse cleanly. It may not burst. It may emit only weak X-rays that blend into the background of the galaxy. If it sits far away, that faint emission becomes fainter still. If it lies behind dense clouds of dust and gas near the galactic plane, its signal can be absorbed or scattered before it ever reaches us. And timing matters too. A burst that happens while no telescope is looking might as well not have happened. A flare that points away from us might never be detected. A quiet magnetar could sit in the Milky Way for thousands of years and never once give us a dramatic moment to notice. So astronomers look indirectly. Sometimes they search the remnants of supernova explosions, expanding shells of gas that mark where a massive star died. If a compact object sits inside that remnant, it becomes a candidate. Sometimes they search for unusual patterns, X-ray emission that is too hot for an ordinary neutron star, or spin behavior that hints at a very strong magnetic field, or sudden, rare events that briefly reveal what was hidden. But even then, the conclusion is cautious, because in astronomy, "we haven't seen it" is never the same as "it isn't there." The sky is too large, the time windows are too short, the signals are too easy to miss. That is why the idea of a hidden population matters. Not just for magnetars, but for how we interpret the universe as a whole. Our catalogs feel concrete, but they are shaped by selection effects, by what our instruments can detect and what the universe chooses to show us. So magnetars may be rarer than pulsars, or they may be more common than we think, simply quieter than we expect. And that twist changes the meaning of every statistic we hear, because the most extreme objects are not always the most obvious ones. Over time, even the most extreme objects begin to change. A magnetar is most dramatic when it is young. That is when its magnetic field is at its strongest, its internal stresses are still settling, and its crust is still learning how to survive under an impossible load. In those early years, astronomically speaking, the star behaves like a system under tension. Energy is stored, then released. Quiet stretches are interrupted by sudden bursts, sometimes, very rarely, by giant flares. It can look like a cosmic fireworks show, but magnetars do not stay in that phase forever. Over time, the very thing that powers a magnetar begins to fade. The magnetic field slowly decays. This does not mean the field disappears, or that the star becomes ordinary. A magnetar remains a neutron star, still dense, still compact, still extreme compared to anything we can touch. But the magnetic energy reservoir is not infinite. And as the field evolves, it loses its ability to twist the star's environment with the same violence as before. The outbursts become less frequent. The quiet stretches become longer. At the same time, rotation changes too. Many neutron stars are born spinning rapidly. But a strong magnetic field acts like a brake. It couples the star to its surroundings through electromagnetic torque, bleeding rotational energy away. The magnetar slows down. This is one reason magnetars often rotate more slowly than many pulsars we hear from regularly. They are not weaker objects. They are objects that have spent energy differently. A young magnetar can be loud because it has energy to waste. An older magnetar becomes quiet because it has already paid much of that cost, and that quietness has consequences for observation. A magnetar that no longer bursts is much harder to detect. Its X-ray emission can cool and dim. Its signals can blend into the background. It doesn't vanish. It simply stops announcing itself. This creates a kind of illusion in our catalogs. We tend to discover magnetars during their active phase, the phase when they demand attention. Then we might assume that magnetars are inherently rare. But part of that rarity may come from timing. We are catching them during the brief chapter where they are easiest to see. When that chapter ends, the magnetar doesn't die. It fades into a quieter life. This is one of the quieter truths of astrophysics. The universe is full of objects that once screamed and now whisper. And there is something strangely calming about that. Because magnetars are often described as monsters, cosmic engines of violence. But their story is still a story of change and limitation and time. Even the most extreme stars do not stay extreme forever. They age, they slow, they cool, they settle. The fireworks end, and what remains is not emptiness, but information. Because the quiet state still carries clues about magnetic decay, about the interior structure of neutron stars, about how matter behaves when it is pushed past every familiar boundary. Sometimes, silence is not the absence of physics. It is the physics continuing, more gently. And sometimes, the clearest signals are not the loudest ones nearby. Sometimes, the clearest signals travel the farthest. Fast radio bursts, often shortened to FRBS, are among the strangest signals ever detected from space. They are not images. They are not explosions you can see. They are brief flashes of radio waves. Extremely brief. Most last only a few milliseconds. In that tiny slice of time, they can release as much energy in radio waves as the sun emits over days or even longer. That combination is what made FRBS so puzzling when they were first discovered. They were short, they were bright, and they came from far away, often from other galaxies. At first, astronomers weren't even sure they were real. A signal that brief could easily be dismissed as interference, a glitch, a human-made artifact. But once multiple telescopes began detecting them, and detecting them from different parts of the sky, the conclusion became unavoidable. Something out there was producing intense radio flashes on incredibly short timescales. That immediately ruled out many familiar sources. Supernovae are powerful, but they unfold over hours, days, and weeks. Accreting black holes are energetic, but their variability usually has structure that lasts longer. Ordinary stars simply cannot release that much energy so quickly. FRBS forced a rethink. Over time, dozens, then hundreds, of bursts were cataloged. Some repeated, others appeared only once. And with every new detection, the same question returned. What kind of object can do this? The key constraints were clear. The source had to be compact, small enough to change on millisecond timescales. It had to be energetic, capable of generating intense electromagnetic output. And it had to be able to act suddenly, without warning. That combination points naturally toward neutron stars. And among neutron stars, magnetars stand out. Magnetars are already known for sudden, powerful outbursts. They can release large amounts of energy in very short periods of time. They are compact enough to operate on millisecond scales. And critically, their magnetic fields are strong enough to reorganize plasma and electromagnetic fields violently and quickly. That does not mean magnetars explain every FRB. Some FRBs repeat in patterns that suggest ongoing activity. Others do not repeat at all. Some appear to come from environments rich in star formation. Others do not. The evidence points toward diversity. Magnetars are likely one class of FRB source, but not the only one. That distinction matters. It keeps the science grounded. It avoids turning magnetars into a universal answer. But even as one contributor among several, magnetars changed the conversation. They offered a real, physical mechanism, one rooted in known extreme astrophysics rather than speculation. And they offered something else too. FRBS turned magnetars into tools. Because these radio bursts can travel across billions of light years, they carry information about everything they pass through. Gas, plasma, magnetic fields, and the large-scale structure of the universe itself. A signal that lasts milliseconds can become a probe of cosmic space. And then, In 2020, one of these bursts came from much closer to home. For years, the Magnetar FRB connection was persuasive, but not proven. It made sense on paper. It matched the timescales. It fit the idea of sudden energy release from an extreme magnetic system. But the strongest FRBs were coming from other galaxies, so far away that we could rarely identify a single object with confidence. Then, in 2020, something changed. A magnetar inside our own Milky Way produced a burst of radio energy so intense that it looked, at least in key ways, like a fast radio burst. The source was SGR 1935 plus 2154, a known magnetar in our galaxy, and unlike distant FRBs that arrive as isolated radio flashes, this event came with context. It was detected in radio, and it was accompanied by high-energy activity consistent with magnetar behavior, X-rays, bursts, the kind of electromagnetic restlessness magnetars are already famous for. For the first time, we weren't trying to reconstruct an event from across hundreds of millions or billions of light years. We were watching a local magnetar behave like an FRB source, close enough to study in detail, close enough to compare across wavelengths, close enough to reduce the uncertainty that distance usually forces on us. It wasn't identical to every extragalactic FRB. Some FRBs are far more energetic than what we saw in 2020. Some repeat in complex patterns. Some appear in environments that don't resemble the region around this magnetar. But that's exactly why the event mattered. It didn't claim to solve the entire FRB mystery. It did something more valuable. It proved that at least one ingredient of the FRB universe is real. Magnetars can generate FRB-like radio bursts. That single confirmation changed the landscape. Before 2020, magnetars cause FRBs was one hypothesis among many. After 2020, magnetars became a confirmed class of source, at least for some bursts, in some circumstances, in some parts of the universe. It also clarified something about scale. A magnetar doesn't need to be in a distant galaxy to behave this way. The physics is local. The engine is compact. The burst is a moment. And if magnetars can do this here, then they can almost certainly do it elsewhere. Under different conditions, with different energies, in environments that may amplify or reshape what we detect. So the 2020 event didn't end the mystery. It anchored it. It turned magnetars from extreme stars that sometimes flare into something more. A source of signals that travel across the galaxy, across intergalactic space, across cosmic time. Magnetars are no longer just extreme stars. They are messengers. By now, magnetars may feel like cosmic monsters. They crack their own crust. They fling radiation across space. They twist magnetic fields until they snap. But the deeper truth is quieter. Magnetars are not monsters. They are what happens when nature follows its own rules all the way to the edge. A massive star runs out of fuel. Gravity wins. Matter collapses into a neutron star, an object so compact that atoms cannot survive as atoms. If conditions are extreme enough at birth, the magnetic field becomes the dominant engine. Nothing supernatural, just physics under pressure. And that is exactly why magnetars matter. Because magnetars are not important only for what they are. They are important for what they allow us to test. They test the behavior of matter at nuclear density. Inside a neutron star, matter is squeezed beyond ordinary chemistry, beyond ordinary solids, into regimes where the equation of state becomes uncertain. We can't build that on Earth. We can't hold it stable in a lab. But the universe can, and magnetars give us observable clues: spin behavior, cooling, bursts, oscillations that help narrow what matter can be when gravity and quantum pressure meet head-on. They also test quantum physics in a way that feels almost philosophical. Near a magnetar, the magnetic field becomes so strong that even empty space is no longer empty in the simple sense. Vacuum polarization stops being a purely theoretical idea and becomes a physical effect that can shape how light travels. That's not a metaphor. That's the universe offering a direct experiment in a regime we cannot reach ourselves. Magnetars also test our models of how stars live and die. They connect the end of a massive star to a compact remnant that can remain active for thousands of years. They may influence how some supernova remnants evolve. They may help explain certain unusual transients. They offer a bridge between stellar death and the energetic signals we detect across galaxies. And then there is the role they play as messengers. Fast radio bursts showed us that a signal lasting milliseconds can cross billions of light years. And the 2020 event in our own galaxy showed that magnetars can produce FRB-like bursts, turning a long-standing hypothesis into something grounded in observation. That doesn't mean magnetars explain everything, but it means magnetars belong in the story of how the universe communicates. So when we ask what magnetars teach us, the answer is not simply, they are extreme. It's that extremes define the boundaries. Black holes teach us about gravity at its limit, about space-time, horizons, and how information behaves in the deepest wells of the universe. Magnetars teach us something different. They teach us about electromagnetism at its limit, about magnetic energy, plasma, and the behavior of matter when magnetic fields become so dominant that they shape everything around them. In a way, magnetars are a stress test, not because the universe is fragile, because the universe is thorough. Nature explores extremes so we don't have to. It builds environments we cannot engineer, runs the experiment for thousands of years, and then lets the result travel to us as light. And when you step back far enough, that changes the tone of the story. At first, magnetars feel like threat, something violent and unsettling. But by the end, they feel more like teachers. They show us that the universe is not random chaos dressed up as mystery. It is structured. Even its most violent events follow a chain of cause and effect. Stress builds, energy stores, fields twist, crusts fail, reconnection releases power. And the fact that we can model any of it at all is a kind of quiet triumph. Because it means our laws of physics are not fragile stories we tell ourselves. They are descriptions of something real. Something that remains true even in the most extreme corners we can observe. That is the perspective magnetars offer. They don't just sit out there, distant and strange. They help define what is possible, and by defining the edge, they help us understand everything inside it. The calmer stars, the ordinary matter, the predictable light, even the space you are sitting in right now. And while magnetars continue their silent evolution, life on Earth goes on. Far from here, magnetars continue their quiet work. They spin, they cool. Their magnetic fields slowly relax, releasing less energy with each passing century. Nothing sudden, nothing urgent. They are still extreme objects, but they are also stable, bound by rules that do not change simply because they are powerful. And most importantly, they are very far away. The universe contains extremes because it is vast enough to hold them, but it also contains enormous regions of calm, long stretches where nothing dramatic happens at all. Both are part of the same system. Stars are born, stars evolve. Some reach extraordinary limits, and others fade gently into quiet states that last longer than human history. None of this is happening to you. The light from Magnetars takes tens of thousands, sometimes millions of years to reach us. What you've heard tonight is not a warning. It is a record, a story already written long before this moment. And while the universe explores its extremes, it does so patiently. Nothing rushes, stars rotate at their own pace. Magnetic fields unwind slowly, galaxies drift, not hurry. There is no deadline in space. You can feel that rhythm if you let it settle in. A slow spin, a long cooling, a steady balance between forces that have been in conversation for billions of years. Your own rhythm fits inside that. Your breathing has a pace. Your heartbeat has a pattern. Both are far quieter than any cosmic event, and far closer. You don't need to track another signal tonight. You don't need to wait for another discovery. The universe will continue exactly as it always has, whether you are watching or not. Magnetars will remain distant. Their outbursts will remain rare. Their lessons will still be there tomorrow and the day after, and long after this night has passed. There is nothing left to solve right now. No mystery that needs your attention in this moment. The universe does not rush, and neither do you. So you can let go of the need to understand anything further tonight. You can let the last details soften. You can allow the edges of the story to blur. Because even the most extreme objects in the cosmos eventually settle into quiet phases. And this is yours. While stars turn and fields unwind, you can rest. The universe will keep pushing its limits. And tonight, you don't have to. Thank you for staying with us until this moment. If you're listening at the end of a long day, allow yourself to let go of whatever has been weighing on your mind. Settle into a comfortable place. Breathe slowly. Let your thoughts drift as the universe continues its quiet motion. There's nothing you need to do right now. Nothing you need to solve. If you'd like, feel free to share your thoughts with us in the comments. We always enjoy hearing from you. Until next time, rest well and sleep peacefully.